your ability to fight infections, including tuberculosis. Steroids sometimes fatal infections and cancers, including lymphoma, happen. As important with it. Alright, so taste, two mechanisms, activated by second messenger system and depolarization. Now, second messenger system, that's going to deal with cyclic AMP as the second messenger. So again, the first messenger binds to the receptor site outside the cell. That's going to activate adenylate cyclase that will move along the inner membrane, and that's going to convert ATP into cyclic AMP. And then cyclic AMP then becomes the second messenger, and it's going to migrate down into the cell to activate a sequential event reactions inside of the cell. So sugars, alkaloids, glutamates, these are those things that can bind and activate the G protein on the inside of the cell. Now, sodium and certain acids can penetrate the cell and can cause depolarization to take place. But either one of these will cause the release of our neurotransmitters that stimulates the dendrites at the base of the taste buds on the tongue. Alright, again, facial nerve deals with sensory information from the taste buds that covers the anterior 2/3 of the tongue. Glossopharyngeal deals with the posterior 1/3, and vagus, it deals with the palate, the pharynx, and the epiglottis. With taste, again, signals are sent to two distinct locations, the hypothalamus and the amygdala. So this deals with salivation, gagging, and vomiting. The thalamus can carry it up to the postsensory gyri of the cerebral hemispheres. And then the orbital frontal cortex, it can integrate what we see and what we smell that gives us the impression of how well or how bad food is going to taste. Alright, here we go back to olfaction, smell. It goes up under the olfactory bulb, the olfactory tract. We're sitting up in the inferior aspect of the frontal bone. You're going to have your cribriform plate. So we got about 10 to 20 million olfactory cells. You got mucous membranes that line there. Now remember the nasal concave. You got the nasal, internasal bone, superior, inferior, and middle. There can be 2,000 to 4,000 different odors that our body can distinguish between based on our ability to smell. If you look at figure 16.7b, again, olfactory smells, you got your hair cells, again, binding sites for odor molecules, and they are non-motile. Olfactory, again, deals with cranial nerve number 1. The axons can collect in the small fascicles and lead by way of the cranial nerve cavity, your cribriform foramen, and in the ethmoid bone. Alright, this is just another diagram that shows the transmission of smell. You see odor, the mucous membranes. You got your cribriform plate. You got your glomerulus. You got your tough cells, your mitral cells, and your olfactory bulb. Smell, again, more sensitive than other our taste. Humans have only about 350 kinds of olfactory receptors. Women tend to be more sensitive to odors than men. And this can be correlated around their ability or their cycles of ovulating. Odorant molecules, again, receptors on olfactory cells. Some of them are hydrophilic, water-loving. Some of them are hydrophobic, water-hating. Alright, we looked at smell. Odor activates our G protein, that then activates our cyclic AMP, our second messenger system. Opens the ion channels for sodium and calcium that plays a role in the release of the neurotransmitters that can trigger the action potential from our pre to our postsynaptic ganglion. Other odors act as nociceptors like trigeminal or pain receptors such as chlorine, capsaicin, ammonia, or methanol. Alright, we talk about pheromones. These are odors that our body gives off. Sexual arousal. Okay, sweat and vaginal secretion affects other people's sexual physiology. The presence of men seems to influence female ovulation. Ovulating females' vaginal secretions contain pheromones called eucarpulins, and males has testosterone levels. Again, our projection pathways, we see olfactory bulb, our dendrites, our mitral and tuft cells. You see our glomeruli that can identify different types of odors. The tuft and mitral cell form axons of our olfactory tract. There it goes to the primary olfactory cortex in the inferior surface of our temporal lobe. There, the secondary destination is the hippocampus or the amygdala, and these fibers can reach back to olfactory bulbs where they granulate cells that can inhibit the mitral or tuft cells. Odor change under different conditions, and these can have an impact on our appetite. This figure 16.8 is just a schematic of the brain, and it shows you the different pathways that we can look at in terms of the insula, hypothalamus, amygdala, hippocampus, and your primary olfactory cortex. Alright, hearing again, a response to vibration of air molecules, motion, equilibrium, orientation. The sensory sense in the inner ear and through a different maze of fluid-like cavities. Again, the fluid is a set of motions and sensory, and the pathways travel by way of wavelengths through the ear canal and vibrating the tympanic membrane. That in turn stimulates the three bones of the inner ear, the incus, the malleus, and the stapes, to generate an action potential. So again, we see sound, vibrating objects. We see tuning forks. Again, they push on other air molecules, hitting the inner eardrum, causing it to vibrate. You can see our round one, the cochlea, that snare-shaped structure. We see the vestibular branch of the nerve. You see your semicircular duct. You see your malleus, your incus, and your stapes. Here we see frequencies, pitch. We hear things in decibels. So human hearing can range from 20 to 20,000 hertz. Ultrasonic is above 20. Infrasonic is below 20. Speech is anywhere from 15 to 5,000, where hearing is most sensitive. Most hearing loss with age ranges from 250 to a little over 2,000. Decibels is the loudness. Prolonged sounds over 90 can cause damage to our ear cavity. So here's the anatomy of the ear. You see your outer, middle, and inner ear. You see your auricle, your helix, your auditory canal. You see your lobule that has a lot of adipose tissue in it. You see your tympanic membrane. You can see your stapes. You see your semicircular canal. You see your round one. And auditory tube. This is where they put tubes in babies when they keep recurrent ear infections, and they put the tubes there. Alright, this is just a picture of the concave, antihelix, triangular fossa helix, and the earlobe. The outer ear, again, a fauna conducting vibrations by way of the tympanic membrane. The pinna directs sound down the auditory canal. Once in the auditory canal, you got your external acoustic meatus, passes leading into the temporal bone. There, it takes a slightly S-shaped tube, and it begins at the external opening, runs about 3 centimeters. You got your cerumen. This is the earwax. It tends to trap impurities, and it plays as a muffler or an insulator. The middle ear contains the tympanic cavity, also contains the tympanic membrane of the eardrum. About a centimeter in diameter, vibrates freely when stimulated by sound, and is innervated by vagus and the trigeminal nerve. We look at our external auditory meatus again, or your eustachian tube. It can normalize pressure. Normally it closes like you're on an airplane, but when you yawn or chew gum, this tends to open it up. It allows throat infections to occur with that interconnection. Again, the malleus, that's the long handle of the bone. Incus articulates with the malleus and the stapes. And the stapes is that foot plate that rests on the oval wonder. We have two muscles in the ear, stapedius muscle and the tensor tympanic muscle. They attach to the two of the bones in the ear, your stapes and your malleus. Just another figure of the middle ear. If you look at the outer, middle, and the inner ear, it contains a middle, inner, outer, and it contains the tympanic membrane, round one, eustachian auditory tube, and as well as the vestibulocochlear nerve. Okay, if we look at the middle ear infections again, auditory tube is called otitis media, very common in children, but kids, they're always putting their hands in their mouths, in their ear. They like to pick up things from other kids that are like pacifiers, so it's easily transmitted. Again, fluid can build up behind that cavity or that membrane, causes vertigo, dizziness. It can lead to meningitis if it's not treated in time. You can do a tympanostomy where you lance that membrane to drain the fluid out. Alright, this is just an anatomy of the inner surface, inferior of the cranial cavity in terms of the temporal lobe, and posterior is going to be the occipital lobe. Here when you look at the inner ear, you have the bone of Lambert. This goes and leads into the temporal ball. You got the membranous Lambert, where you got fluid field, endolymph, and perilymph. Endolymph resembles the intracellular fluid. Perilymph is the extracellular fluid. Here you got fleshy tubes lining the bone at Lambert, but you see the snail-shaped component of the inner ear. Alright, the Lambert, vestibular, and 3 semicircular ducts. You see your vestibular nerve, cochlear nerve, facial nerve. You're going to see your ampulla, those little swollen regions. You see your saccular on the right, your eustachial on the left. You see the cochlear, that like little mushroom-shaped structure. Again, the inner ear has the scaly tympanic inner chamber. It has the perilymph, and the sacrovestibular also has perilymph. It starts at the oval ulna and spirals up to the apex. The scala media has endolymph. Now, perilymph, cerebrospinal fluid, endolymph, intracellular fluid. There it contains the the spinal organ, or the organ of cortes, or your acoustic organ. So it deals with innervation of vibrations in terms of the cranial nerve number 8. Alright, figure 16.13 is just a diagram of the inner ear. Your spinal organ again has hair cells and supporting cells. It has a gelatinous material called the tectorial membrane, or your microvilli called stereocilia. You got the spinal organ that has the inner hair cells, about 3,500 of those, deals with hearing, and the outer hair cells, they deal with precision. And they can identify and detect the different kinds of frequencies. Alright, figure 16.14 is just a scantron of the cochlear hair cells. The tympanic membrane again, you got your ossicles. They create a greater force per unit. They are under the area of the oval ulna, and they can overcome inertia by way of the perilymph. Also, the ossicles and their muscles have a protective function within the inner ear. You got your tympanic reflexes again. Doing loud noises, the tensor tympanic pulls the tympanic membrane inward. It tenses up. The stapes muscles reduce the motion. It muffles the transfer of vibration from the tympanic membrane, leading to the oval ulna. Here, the middle ear muscles also help coordinate speech and hearing. Alright, if you look at vibration of the ossicles again, about 20,000 times per second, you see your basilar membrane. Here you see the outer ear as it comes in, the middle ear where the air and the fluid compartment of the inner ear. So again, the second tympanic membrane helps to innervate the round window. Stereocilia again bathes in potassium fluids. The resting membrane potential amount is 40 millivolts, but it can be depolarized up to 80. They are embedded in the tectorial membrane. Your stereocilium again is the outer inner hair cells. They have small amounts of proteins. They're tip linked. They interact with the ion channel. The tallest stereocilium is bent when the basal membrane rises up and reaches toward the tectorial membrane. Potassium flows in, causes depolarization, and this stimulates the release of our neurotransmitter that generates an action potential within the cochlear nerve itself. So this just shows you the flow of the potassium channels when a bending of these stereocili when the gates are closed and the potassium gates are open between the two diagrams. Alright, loudness, amplitude, again, the intensity of the stimulation on the cochlear vibration. Soft sound produces relatively slight up and down motion. Louder ones triggers more of a high frequency type of action potential. How we interpret low pitch sound from loud sound. Again, you got pitch, depends upon at the basal end is attached and narrow and stiff. The brain interprets signals as high pitch. At the distal end, it detects it as a low pitch sound. Alright, here again it shows you a diagram of the color spectrum between high and low frequencies. The cochlear turning increases the capability of the cochlear to get perceived sound or receive it. The outer hair cells, they can shorten, reducing the basal membrane mobility. So this allows the brain to distinguish between more or less active areas of the cochlear. Whereas the pons has an inhibitory effect on the inner hair cells, and they can have a increased contrast between regions of the cochlear that's stimulated. Alright, when we look at deafness. Alright, deafness deals with hearing loss. We have two types, conductive deafness and sensorineural. With sensorineural, we have compromise of hair cells, and here it eliminates the transmission of impulses. So, again, when it's concerned with hearing, factory workers, construction, musicians, where they are around loud noises. Conductive type, this is due to infection. Osteosclerosis is hardening of the ossicles where they do not vibrate properly, or damage to the tympanic membrane that perceives the flow of vibrations as they're coming from the outer to the middle to the inner ear. The projection of auditory deals with the cranial nerve number 8, also the cochlear nerve, and your vestibular cochlear branch. They reach the ears, and they send to both sides of the pons. There, at the end of the cochlear nerve, they can form a synapse with the second order neuron that can travel up to the superior olivary nuclei. Here, it can function as a biangular hearing, comparing signals from the right, binaural hearing from comparing sound on both the right and left ear. So when they do auditory hearing, they test one ear, then they test the next ear, and to see if there may be some weakness in one as compared to the other side, left or right. From there, you got your inferior colliculi of the midbrain. It helps to locate the origin of the sound, process the pitch of it, and it mediates the response that's going to occur. If it has to go up to the somatosensory area, it has to pass through the thalamus. And here you see the fourth order neuron where it deals with conscious perception. It can cross over, and it can also be affected if damage has occurred, affecting unilateral hearing loss on one side. If you look at figure 16.18, it just shows you a pathway as it comes in from the cranial nerve to the cochlear nerve or the pons, forms a synapse. It begins to travel up the sensory olivary nuclear pons up to the inferior colliculus. Then it travels by way of the neck muscles onto the auditory reflexes of the head, turning in the direction of the sound. Alright, this is just another diagram of the cross section of the brain that depicts the transmission of cranial nerve number 8 to the cochlear and your semicircular canal. Equilibrium again coordinates balance, three-dimensional orientation in space. The semicircular angular acceleration in our chambers deals with static and linear acceleration and equilibrium. Static, again, perception or orientation when the body is standing still. Dynamic, linear, is when the body is in a straight line, maybe on an elevator, or angular deals with changing the rate of activation. Here we see the macula, saculi, and utracele. The saculi, it lies vertically within on the wall of the sacral, and the utracele is horizontal on the floor. Olynthus, this is calcium carbonate proteins. They add to the weight of the inertia and enhances the sense of the gravity and motion. Here we also see kinocilium is embedded in that gelatinous authentic membrane. So this helps us to perceive gravity and motion. Static equilibrium, when we tilt our head, the direction of the membrane sags, bending the stereocilium, and it causes the hair cells to be activated. Dynamic is in a curvilinear acceleration as the olynthus lag behind, causing the stereocilium stimulation of the hair cells. Based on this, the nearly vertical, it responds to vertical acceleration and deceleration. Rotary movement, again, three-dimensional semicircular ducts. Endolymph, again, the swollen region, a dilated sac called the ampulla, and your cristae appullaris. All right, this consists of a mound of hair cells and supporting cells. Cristae appullaris, again, your hair cells, so your stereocilium. You can see that it's buried within the mound of the gelatinous membrane called the cupula. Here it can causes ducts to be stimulated by rotation in different planes. A lot of times when we see skaters, when they spin, instead of getting dizzy, they fixate their eyes on a particular object, and it helps them to maintain focus and not. If you look at figure 1621, it's a diagram that shows you the anatomical location in the brain of your spatial orientation, your compensatory eye movement, motor coordination, and postural reflexes. Here we can see that the hair cells of the macula, sacula, and utracilla, and your ducts are innervated by part of cranial nerve number 8, the vestibular branch of it. There, the fibers form a complex with the four vestibular nuclei, the pons, and the medulla. So therefore allows the right and left nuclei to receive input from both different ears. Now we're going to have 5 target areas that we're going to look at. Cerebellum, the nuclei of the oculomotor trochlea abducens, reticular spinal cord, and the thalamus. So as we look, the cerebellum, the somatocortex, it deals with integrating vestibular information, muscle tone, head-eye movement. Oculomotor trochlea abducens, 3, 4, and 6. They can fixate on the distance at object while walking. Reticular postural changes and breathing. Spinal cord, it goes through the vestibular spinal tract of the spinal cord, innervates the extensor, anti-gravity muscles, and the thalamus. Again, relate to the cerebral cortex that control head and body movement. Alright, sight, vision, perception of an object. Light is perceived on wavelengths from 400 to 7. Ultraviolet is less than 400. Infrared is anything above. 700 does not warm the tissues. Less than has a lot of energy. Since it's ultraviolet, it can destroy large size molecules. Alright, this is the anatomy of the eye, the eyebrow, pupil, eyelash, sclera, the white part, the tarsal plate is the little rim, inferior aspect, the corner of the eye, medial commensurate on the medial side, you got a lateral one, and you got a palpebral sulcus. That's the little frigid skin lines under the eye. Again, what are the accessories? What they do, eyebrows enhance facial expression, getting them arched from that standpoint. It runs perspiration from in the eye. The eyebrow, again, blocks foreign things from entering, gives us our blink reflex. Tarsal glands secretes oil to keep the eyelashes of the eyelashes from sticking, tear evaporation, and it helps keeping debris out of your eye. You can see the conjunctiva, you see the white part around there, the cornea. You can see the superior rectus muscle sitting on top, the lateral muscle sitting on the side. We can see the fat on the superior and inferior aspects of the eye. It's really innervated by a iris that enters into by way of the blind spot of the eye. The lacrimal apparatus for tearing, and you see how it goes from superior at the corner of the eye to inferior. The nasal, the nails of the nasal passageway, and it's internal, so when we cry a lot, it runs, the overflow rolls over into our nasal cavity, and it runs out our nose. Again, it helps to lubricate, it brings oxygen in, it secretes a bactericidal lysozyme to kill and ward off infection. You got 6 extrinsic muscles, that means they originate outside, superior, inferior, lateral, medial, superior, and inferior oblique. The internal ones are the intrinsic ones, again, cranial nerve number 4, innervates the superior oblique eye, 6 innervates the lateral rectus, and your 7 real eye, I don't like you around me. Alright, and then the third innervates other 4 intrinsic, extrinsic muscles. 6 innervates the lateral rectus. So as you learn this diagram, look at the muscles of the eye, and then based on their location, it will determine if they rotate the eye medially, laterally, inferior, or superior. This is an anterior view of the accessory structures of the eye. So again, medial rectus, lateral rectus, superior oblique on the top, inferior oblique, inferior aspect of the eye. You see your blind spot, you see your optic nerve, you see the yellow portion is your nerve and your vein. You can see the cornea, the iris, the pupil, the lens. You got 3 layers of tunics of the eyeball, wall of the eyeball. Optical components emit and focus light, and the neural part is the retina. And if you hear about retinal detachment, that occurs in sometimes diabetics that has very high elevated blood sugars that they don't keep under control. Alright, you got your tunic, fibrosa, vasculosis, and internal. The internal, you got the retina, begins at the optic nerve. You got the vascular or uvea, the middle portion is very vascular. You got your extensive coral cord that submits blood supply to the area. The coral cord is highly vascular, secretes aqueous humor. It supports the lens and the iris. The cornea, that's the transparent region of the modified sclera in front. It allows light to come in. Again, aqueous humor. Again, viscous and aqueous humor. The pressure nodes determine if we have glaucoma. But the optical component is transparent. It reflects light rays. It has the lens, your viscous, and your aqueous humor. If you look at figure 16.26, it shows you the aqueous humor is released by capillary bodies. You got your posterior chamber, passes through the pupil and travels into the anterior. Then you see the reabsorption of the sclerovenous sinuses. You see your body, you see your anterior chamber, the cornea, you see your ciliary muscle and your ciliary body and ciliary process. Against the lens, they can flatten out, they can tighten, they can compress. They can change shape based on how much light they need to let in or do not need to let in. So again, changes in the shape to help focus the light. You got your suspended by your suspensory ligament from the cerebral body. Your viscous humor is gelatinous or jello-like. It fills the space between the lens and the retina to help cushion and help collapse from taking place. Again, when we look at the retina optic vessels, you got your orbis serrata, the jagged edge of the anterior edge of the retina is pressed against the rear of the eyeball and by a viscous humor. You got blurred areas of vision that can cause blindness if you get damage to the retina or complete blindness if it detaches. Remember that retinas are outgrowth from the secondary brain vessel diencephalon. Macula lente patch of cells for visual axis of the eye, the fovea centralis, and the natural the macula lente, and your blood vessels that feed the retina. Ophthalmoscope is how we look into the eye. A lot of times when our blood pressure is elevated, you can see a very high amount of blood vessels in that region. Here you see your fovea centralis, macula lente, optic disc, anterior lobe. Again, they detect detailed images due to the package of the receptor cells. Ophthalmoscope is the aid to help you find that. Alright, if you look at the figure 16.28 again, you see the ophthalmoscope too. It examines the blood vessels in the eye. It examines the presence of attached or detached retina. You can see again your arteries and your veins. The blind spot, again, visual field in the brain field. If you look at the dot and the X, again, it helps us to the brain field in the green bars across the blind spot area. Cataracts, again, cloudiness of our lenses. Treatment replacing the natural lens with a plastic one. Smoking, ultraviolet rays increase due to elevated diabetes. Glaucoma, elevated pressure in the eyes by looking at the viscous humor or the aqueous humor can cause depth of the retinal cell that can compress the vessels, lack of oxygen, and this can lead to blindness and then real cloudy hue over the eye. Again, we got our pupillary and Alright, light passes through the lens to form a tiny inverted image on the retina. There, the iris diameter is regulated by the amount that comes in. You got constrictors and dilators. Smooth muscles and circular pupillae can cause parasympathetic stimulation to make them narrow. Pupillary dilator, again, the mild epithelial cells can stimulate the sympathetic, can cause them to widen. Again, pupillary constriction and dilation occurs when the light intensity changes. Photopupillary reflex, again, based on the brightness of the light, can signal to be a pretectal region of the midbrain. It excites the parasympathetic, stimulates the oculomotor nerve that travels to the cerebral ganglion. From there, the fibers stimulate the pupils to constrict. Refraction is bending of light. The speed of light can be 300,000 in a vacuum but slower in air. Refractive index, the medium in which you measure on how the object retards light rays relative to the air. Okay, so again, the angle of incidence can be at 90 degrees. So the greater the refractive index and the greater the angle, the more refraction of the light is going to take place. So again, we look at the cornea. We see how light comes in. Light striking off the center is bent toward the center. Aqueous humor and the lens do not greatly alter that flow of light through it. So again, the lens become more rounded, increased refraction for near vision to take place. Again, emmetropia is a state in which the eye is in a more relaxed state. Light rays coming from that object are essentially parallel. Rays coming from closer objects are too divergent to focus on without an effort. Convergence uses visual axis toward the object. They constrict the pupil. Light rays and reduce spherical aberration. You can get blurry edges. With accommodation of lens, you got the ciliary muscles contract, your ligaments slacken, suspensory ligament slackens up some, and the lens will become more convex. Lightly refracted, they're more strongly focused onto the retina. Near-point vision, closest of the object can be, and still come into focus depending upon the age of the individual. Right. These are just pictures of the lens shape in slide 16.31b. Emmetrophic, how it hits on the fovea. The pupils are dilated. You look at the relative thickness of the lens and the constricted of the lens in terms of meiosis and accommodation. Here we look at emmetrophic distant vision as compared to near vision and accommodation, where the lens is thin in diagram A but thicker in B. Alright, some of the defects, again, we see emmetrophic is normal, hyperopia is farsightedness, and myopia is nearsightedness. If it's uncorrected and compared to corrected, you use a concave lens. For farsightedness, you use a convex lens. Alright, again, the retina converts light energy into actual potential. Your neural components, you got photoreceptors, rod is black and white, cones is color vision. We see our ganglionic cells that we look at, and in bipolar, your first order neurons, they synapse the dendrites with the rods and the cones. The second order with the ganglion cells, which are the largest in the retina, and they're arranged in a single layer next to the body's vitreous humor. So if you look at the next diagram, we can look at the light absorbing rays. Again, rod cells, night or scopic vision. The outer segments, you see layers of membranous discs studded with proteins or rhodopsin, the pigment for our vision. Right, cones are color vision. The outermost segments, the discs with pigments are plasma membrane enfolding, but they do not detach. Right, this is just a histological view of the rods and the cones and transduction of light toward the retina. Okay. Here is a diagram of the figure 16.34, where you see the photopigments, rod receptors, transmission of the rod signals for black and white. In the dark, then in light, you get color. It goes from the horizontal through the bipolar, through the amacrine cells, to the ganglion, onto the optic nerve for vision. Alright, this slide just goes through what I said. The horizontal and amacrine cells are present, but they do not form separate layers with interacting with the retina. The horizontal and the amacrine cells form horizontal connection with the rods and the cones. They can enhance the perception and contrast of the object based on the light intensity. Again, the retina receives blood from the astrocytes, which are a set of neuroglial cells that we talked about several chapters ago. Again, opsin and retina or retinae are the pigments that help to give us vision. Vitamin A is needed for normal vision to take place. Alright, so again, we absorb peaks of wavelengths and get different colors based on the wavelength pattern. Alright, again, the cones contain photoopsin, iodospins, retina more the same as the rods. Opsin, again, contains amino acids and are affected by the wavelength of light. Alright, again, we can look at the diagram. You got the transretinal and the cisretinal in terms of being bleached or unbleached. Light changes, rhodopsin in dark. Alright, in dark, the retinal is bent. It's in the sense retinal. and optic and retina are together. But when light comes in, the cis is going to straighten up. It becomes the trans. Bleaching is going to take place, and this is what color is going to occur. Alright, so these are just diagrams, figure 16.38. And you can look at rhodopsin absorbs no light. The rod cells release glutamate. Bipolar cells are inhibited. No synaptic activity occur. And no signal in the optic nerve fibers occur in A. In light, the glutamate secretion is stopped. The bipolar no longer is inhibited. They release a neurotransmitter. They stimulate the optic nerve. Light travels to the retina, and we get color vision. Alright, so again, this slide talks about the bipolar cells inhibited by glutamate, excited when secretion stops, but in the light, glutamate is going to be inhibited, and the neurotransmitter is going to be released, and the other cells are going to be excited for light vision. Okay, again, generating optic nerve signal. Alright, light adaptation, walking out into the sunlight, the pupil's constriction reduces light intensity, color vision, and acuity below normal for about 5 to 10 minutes. Then it begins to gradually become more functional. The rods are going to become bleached and become non-functional, and the cones take over. Again, in the night vision is just the opposite. 1 to 2 minutes in night, the scopic vision begins to function. 20 to 30 minutes, then you can see a generator rhodopsin, and sufficient for the eyes to reach maximum sensitivity. Okay, with dual vision, it takes one type of cells and neural circuit for sensitive night vision to take place. Alright, this is just a figure 16.39A goes to scopic vision and photovision, photo-optic system. So again, with the dual visual system, the extensive neuronal convergence, 600 rods, they can interact on one bipolar cell, results in high degree of spatial summation. And again, the ganglion cells receive information on the retina, reducing only coarse image. Edges of the retina have space rods on them, low resolution system only, and they cannot resolve fine detailed images, and this is what happens in dark. The fovea non-neuronal coverage have the fovea cone, private like in the brain, but the high resolution, little spatial summation, less sensitivity to dim light. These are color vision, short wavelengths, peak sensitivity at about 4, medium about 531, long is about 580. Violet 400, blue 450, blue green 5, green 500, orange 625, and 675 red. Alright. So again, we look at most males are colorblind. But if you look at the diagram, see can you find the red or the green dots. Occurs 8% of male, 0.5% of females, a sex-linked trait in terms of color blindness. Stereoscopic vision is depth perception, requires 2 eyes, overlapping fields, looking at the same object from a different angle. Panoramic vision, having eyes on the sides of the head like horses and rodents. Fixation, looking at an object within 100 feet. You view it more slightly at different angles, provides the brain with information based on that fixated point on that object. And this is just a figure that in 14.2. Alright, our pathways again, optic chiasm, the 2 optic nerves you can see on the inferior aspect of the brain. You got bipolar cells of the retina. They form a second order with the ganglionic cells. Hemidecussation is half of the fibers cross over to the opposite side of the brain, and the chiasm slits to form the tract. And there's going to carry the information to the different halves on each side of the retina. Again, we see our optic tracts. Again, third order goes from the optic radiation through the thalamus to the primary visual cortex and occipital lobe. The optic fibers project to the midbrain, terminates in the superior colliculi that controls visual reflexes of the extrinsic eye muscles and the pretactile that causes or influences the potopupillary accommodation reflex. Alright, again, primary visual cortex, again, association areas, location, motion, color, boundaries, again, recognize printed words, in terms of the primary visual cortex. That ends this lecture on chapter 16.